Okay, so today we're going to continue our discussion of the formal structure of Maxwell's equations. We're still in real space. I titled this In Real Space and Reciprocal Space because to me this is sort of the important concept I kind of want to get to. But there's a lot of structure to Maxwell's equations we have to know as prerequisites to QED. And it's mostly a review, and we're doing it in a very formal way, which is how you need to know it for QED. And a lot of this can be done in real space and then converted into reciprocal space. So I want to persist, and we will persist with our work in real space and then convert to reciprocal space, right? So today we're on the big topic of gauge invariance, and this is an important issue. It's a fascinating issue, and I'm not sure how many lectures we're going to do on it, but we'll at least do, this one is absolutely critical prerequisite lecture. The subsequent ones will be important and interesting, but less and less critical as a prerequisite. So this time, this lecture, it's really just the basics of what we mean by gauge invariance in real space. So let's begin. So as has become my habit, I've now created a bit of a mind map for this lesson. So we want to start with Maxwell's equations themselves. Again, these are all vector fields that I write without vector notation. I've gone through this before. And Maxwell's equations we've talked about in detail, and we're comfortable with them. I've written them as the two divergence equations on top and the two curl equations on the bottom. An alternative way of doing this is to write the two source equations, right? This is a source equation and this is a source equation, and pair them up and have the source equations and the sourceless equations paired up, right? We could pair those two up. That's another way of pairing them up. But either way, you have to understand that we're dealing with divergence equations, curl equations, equations with sources, and equations without sources, and there are 4 of them. That's the important topic to nail down right now. And we've also prepared ourselves with the notion of the vector potentials, the vector potential and the scalar potential. And we understand that the electric field can now be defined in terms of the vector and scalar potential, and the magnetic field, a little simpler, it is just the curl of the vector potential. Now, what we did a little bit last time, I made a proof of how any magnetic field can be derived from the curl of some vector field. And that proof actually had a step in it where we determined that the z component, I think I chose the z component. You could have done the proof with any of the components. But I think I found, I invented a condition where the z component of the vector potential was 0. And inside that process, I exploited something called gauge invariance. And the notion was that I could add to A any gradient of a scalar function, where f is a scalar function of space, x, y, z, and time, or r hat and time. And as long as that was a gradient of a scalar function, I pick some scalar function, calculate its gradient, add it to A, the curl against A would still be B, but the curl against the gradient is 0 because the curl of the gradient of any scalar function always equals 0. So I exploited this fact in that proof. But what's interesting is this is a very profound statement that, and it's actually, it should be confusing, right? You should be confused by this in the sense that if you were just told that I can find a vector field A that gives you a magnetic field B, you think, okay, this is a physical thing. This must be a physical thing too, because a simple process on this physical thing gives you a physical thing. But now we see that A has a problem. It is ambiguous, right? There are many different A's which satisfy this relationship. But B is a physical thing. So B has to be unique, right? So on this side, we have something that's unique, but it's defined through this potential formulation by something that's ambiguous. And I'm not an expert on the history of physics. I do find it kind of fun to see how these ideas were created. But this was a big puzzle around the turn of the last century. So between the 1800s and the 1900s, this was like a real question that people scratched their heads over. And ultimately, the answer that has been settled on, right? The settled science in the sense that this is the way we describe it. People know that there's some questions about it, but those questions are very rarely really problematic. But it goes like this. Since the force on a particle, which has to do with the acceleration of a particle, which has to do with motion, right? So force goes to motion, and this equals the charge on a particle times V cross B, right? So the way we created this notion of force is through the magnetic field. The notion of force is tied to motion, and what is physics if not the study of motion? So because of this, we want to call B real, meaning it exists, not real numbers, but it exists, right? It's actually something in the world. Now this is all really weird because it's still a field in space, and we're sitting in space, we can't taste it, we can't see it, we can't touch it, and that causes problems with people. But what we can see is things moving, right? So B is real because it immediately gives us something that moves through this relation. Now, there's a lot of problems with this, but that's the general idea of this ambiguity. Because A is ambiguous, we are going to say that it is not real. And because B is not ambiguous, we are going to say that it is real. And we'll fine-tune this a little bit. And of course, quantum mechanics comes in and causes trouble with this entire theory, with this entire philosophy, this entire ontology, I guess is the way to say it. Ontology is sort of the notion of what is real and what is not. It's a philosophy concept, though. It's not a physics concept, and I'm certainly no expert in it. But the point is we are going to adopt the position that A is a mathematical notion that helps us understand how to model B. Likewise, V is a mathematical notion that when combined with A helps us model E. Right? So for the purposes of this lecture, that's the ontology we're going to adopt. All right? And it's the standard ontology. It's not like some weird version of things. Okay, so now that we've gotten the potential formulation down and we have Maxwell's equations down, right? Now we want to ask the question, well, what if we substitute the potential formulation into Maxwell's equations, right? And we can see a couple things are definitely going to happen right away. One is, since the potential formulations already have derivatives, right? Everything is a derivative of something on the right-hand side here. And Maxwell's equations are all derivative equations. We're going to get an additional derivative. So where these are all first derivative expressions, we're going to end up with second derivative expressions. So let's just do it. So the divergence of E is 1 over epsilon naught times the charge density. So here we write that down. The divergence of E, this is E now, right? This is the potential formulation for E right here. And voila, we just have to calculate the divergence of a gradient. Well, that's the Laplacian of, remember, this is a scalar field, so it's the Laplacian of that scalar. And the time derivative of A is the time derivative of a vector field. You do that component by component. And you end up with this expression, the opposite of the Laplacian of the scalar minus the time derivative of the divergence of the vector potential equals the source term. The divergence of the vector potential comes by distributing this divergence right into here and then swapping the derivative orders, right? So that's what gives us this. So that's check. That is Maxwell's equations. That's Maxwell's sourceful equation written in terms of the vector and scalar potential. So now we can turn to this one here, or we can turn to now the divergent. Which one are we going to turn to? I guess we can turn to the divergence of B equals 0. Well, that's really easy because that's just the divergence of the curl of the vector potential. We actually use this to define the vector potential. So this is automatically satisfied via the very mechanics we use to create the notion of the vector potential. We actually used the divergence of B equals 0, this third Maxwell equation, or I guess this second Maxwell equation, depending on, I guess, how you order them. We use this to define the potential. So we learn nothing new there. Likewise, we learn nothing new from the curl of E equals minus the time derivative of B, because we use that to understand and create the notion of the scalar potential, right? So the curl of E, right, this is E here, is minus the time derivative of B, that's B here. That's automatically satisfied by the very definition of how V and A work. And you can see, if you take the time derivative of the curl of A, right, the time derivative of the curl of A is going to cancel with the curl of the time derivative of A. You're going to get it on both sides of the equal signs. Those will cancel. And then all you have left is the curl of the gradient of V. And of course, that's 0 because the curl of a gradient is 0. So this is automatically satisfied. So there's nothing new there. It's all part of our definition of what the potentials are. That was from our previous lessons. So these two guys don't really give us anything new. The third one, however, does. So basically, the two equations that have sources in them give us new information, or are actually still part of what's left over that has. Well, I guess it gives us new information, right? So this one is the how does it work? This one is the curl of B, right? There's the B in there, and then this is the time derivative of E. And that's what this is, right, in potential form. And then if you wrestle with this a little bit and you use your vectors identities, the curl of a curl is equal to the gradient. The curl of something is the gradient of the divergence of something. I guess I'm being a little inconsistent by putting that vector notation there. Remember, this is a vector potential. You just got to know A is a vector and V is a scalar, right? I'm not going to throw vectors on every A and just it becomes a mess. It becomes a mess when you don't have a nice font typesetting, right? So yeah, you just got to know. So this is a gradient of. So this will be a scalar because it's the divergence of a vector, and that's the gradient of a scalar, which is a vector. This is the Laplacian of a vector field, so that's a vector. Notice that the Laplacian of a vector field is a vector, but the Laplacian of a scalar field is a scalar. Right? So you need to understand that. And that comes from the vector identity that links the curl of a curl to these two things, right? And these vector identities are expressed two ways. Sometimes they're expressed as the Laplacian equals the gradient of a divergence minus the curl of a curl. Sometimes it's the curl of a curl equals the gradient of a divergence minus a Laplacian, whatever. But you do have to know that this vector identity exists. And then this is just a distributing the derivative operator into the time derivative operation into this bracket. And you get the time derivative of the gradient of the scalar V, and then you get the second time derivative of A, which I write with these two dots. So this is actually a new equation. And ultimately, this leads to the compression of all of Maxwell's equations, right, where these two are compressed by the very definitions of A and V, and then these two are compressed just as we've executed them a moment ago, and you're left with these two guys right here. These are now Maxwell's equations in potential form. And so this is where we're going to start our motivation of this notion of gauge and exploiting the ambiguity of A and V. So when I first learned this subject, I didn't like it very much. I was uncomfortable because they didn't do enough hyperlinking for my taste. So I'm going to do all the hyperlinking for you. And the issue is, when we looked at these two, that Maxwell's equations compressed as two second-order differential equations, as opposed to four first-order differential equations. It's hard to call that a compression, by the way, right? Because two second-order differential equations with a lot of scribbles is kind of equal to four first-order differential equations with fewer scribbles. I mean, it's not really compression. It's just in a different form. But when we look at these, we say, okay, these are differential equations. We're going to solve them. Well, what do we have a scalar equation and a vector equation. The scalar equation, the Laplacian of a scalar is a scalar. The time derivative of a divergence of a vector field is a scalar, and the charge distribution is a scalar. So this is a scalar equation. The problem is, and then this is a vector equation for opposite reasons. A is a vector, the Laplacian of a vector is a vector, the second time derivative of a vector field is a vector, J is a vector field, a source vector field, the gradient of a divergence, well, the divergence is a scalar, the gradient of a scalar is a vector, etc. So anyway, the point being that these are second-order differential equations, but they're complicated by the fact that they're coupled, right? You have V, this would normally be an unknown function V and an unknown vector function A, and it's coupled with this, which is an unknown vector function A and an unknown vector function, scalar function V. So normally the way you'd kind of do this is you solve one in terms of the other, and then you substitute into the remaining equation, and you can imagine how difficult this might become for any given circumstance. However, we're working in a very formal, rarefied environment right now. And we've already learned something interesting. We've learned that A is ambiguous. It's ambiguous. And so is V. Did I mention that V was ambiguous? Did I point that out yet? Hold on. No, I didn't. I need to explain that A is ambiguous up to the gradient of a function f, right? But that shows up in here because you end up with, because for the E field to be the same, remember this whole thing depends critically on the fact that B remains the same. Well, the same is true for E. E has to remain the same if you change A. But if we change A here, we get plus the gradient of f, and so we've actually added the time derivative of the gradient of f. So in order for E to be the same, we have to adjust V. V has to become V minus the time derivative of f, right? Because you'll now have the gradient of V, which is what this term is, and then you'll have the gradient of the time derivative of f, and you have that minus sign here, which cancels that minus sign here. So you have so it ends up being you add a term that's plus the time derivative of f, and it'll be plus the gradient of the time derivative of f, which will cancel the minus gradient of the time derivative of f here. So V is ambiguous as well, but it's ambiguous based on the same f. So once you pick f to change A, the same f will change V. So A and V are not independently ambiguous, but they're both ambiguous based on choosing f. Once you choose a function f, choosing f is called, if I choose f, it's called gauge fixing. Gauge fixing, right? But it establishes V as well as A, right? It establishes, well, let me put it this way. If I choose f, I'm converting from one gauge A to another gauge A prime, right? So I would write it down as V prime equals V minus the time derivative of f, and A prime equals A plus the gradient of f, okay? So when I'm down here, I want to ask myself, okay, so wouldn't it be nice if I could use that ambiguity of A and its attendant ambiguity on V, could I get it so that the divergence of A was 0, and then this term would go away, and all that would be left would be the Laplacian of V equals this source term. So it would be an inhomogeneous Laplace equation for V. Then that's simple to solve in principle. Remember, this is very formal, so I'm assuming we can solve that in principle, and then I can substitute that into this equation right there, and now I have just a wave equation for A, right? Because this is sort of a wave operator, right? This gives me the wave equation for A, and this just becomes a sort of inhomogeneous wave equation for A, which could be solved in principle. But it's uncoupled to V, right? Because I now know what V is. I've solved for V, and V goes away as an unknown. So that would be nice if the ambiguity for A allows it. And that's the part I had trouble as a student, right? As a student, they just said, oh, because of the ambiguity of A, we can assume that this equals 0, and we call that the Coulomb gauge. But the problem with this, and the problem that I didn't understand very well, was that, well, the Coulomb gauge, I mean, in order to have a gauge, I've got to fix it. In order to fix it, I've got to have F, right? Well, what's the F that gives me the Coulomb gauge, right? I had trouble understanding that I don't need to demonstrate an F. I just need to prove that given any vector potential, I can always find an F to convert it to a new vector potential A prime, such that the divergence of A prime equals 0. And all I need to know is that there exists an F that can do that, right? And, okay, fair enough. So I'm going to show you this proof, right? It's not a long proof, and actually some books do this. I just was not lucky enough to have that book, and I was always confused. I just sort of was given the presumption. It does take a little time to do, and there is a lot to cover in an EMM course, so I have that sympathy. Now, likewise, there's another choice you can make, right? Can I use the ambiguity of A and V to make this term go to 0, right? Can I make del the divergence of the vector potential plus 1 over c squared times the time derivative of the scalar potential, can I get that to go to 0? And if I could do that, well then, what would happen now? Well, this term goes away, and I just get this very much simpler wave equation for A. It's just a straight-up wave equation for A. Inhomogeneous, granted, which definitely makes it hard, but it's still just a wave equation for A. And if this expression in here actually equals 0, then the divergence of A is equal to minus 1 over c squared v dot, right? Which now would become, if I substituted that into here, I would get minus 1 over c squared, or I get plus, I think. It would end up being a plus, right? This would cancel with that. You'd end up with plus 1 over c squared v double dot, right? And that becomes that there is exactly the same as this operator, right? It's the Laplacian and the second time derivative coming in at the opposite sign. So now I have a wave equation for V also. And notice they're also decoupled, right? I have no expression of V here, and I have no expression of A there. So this choice completely decouples both equations, and they're both the same equation. One is a scalar wave equation for V, and one is a vector wave equation for A. So that's another question. Can I make a choice of gauge such that this equals 0? And the answer is, in both cases, a pretty simple yes. And it's simple to see that you can always find a gauge function f that does this. So let's have a quick look. Let's have a quick look at the condition where the divergence of the gauge, we'll call it A prime. This is the expressions in terms of A, some vector potential A. This is going to be true, and when we solve these equations, if we literally solve these equations, we would discover that we would need some additional condition to nail down A. We would end up with some it's partial differential equation, so we would end up with arbitrary functions as constants that we would have to nail down somehow. Well, let's see if we can nail down those functions. That's equivalent of choosing an f, right? We can choose this f, and if we chose this f aggressively, then we nail down all of the variance, all of the unspecified constants of this partial differential equation. So can we find a condition where the divergence of A is 0? Can we find an F where the divergence of A is 0? And if we, I guess I rewrote these. If we did, this is what Maxwell's equations reduce to in potential form, right? Laplace's equation for V and inhomogeneous wave equation for A, where now the V part can be immediately substituted from the Laplace equation. There is some interesting facts here, right? This turns out to be what they call instantaneous, meaning V, notice this is all spatial, right? So V is going to be something that changes instantaneously with time, meaning as the charge density, if it changes, because it's a function of time, remember charge density is going to be a function of R and T, right? As the charge density changes as a function of time, V changes instantaneously all throughout space, right? Because there is no time derivative term here. And that's an interesting problem that has to be fully understood, which we'll talk about later. But also if I choose this gauge here, or when I say choose a gauge, meaning I find a gauge function that creates a gauge transformation where the new gauge has this property, which we call the Lorentz property. Well, I guess it's not called the Lorentz property. This is called the Lorentz gauge. Lorentz gauge. This is called the Coolant gauge. Right? Meaning I found a function f that converts the vector potential into a new vector potential where this property is true. And I found a function f that creates a vector potential where the new vector potential has this property. And when I do that, you end up with, like I said, this symmetric pair of wave equations, one of which is scalar and one of which is vector. So now let's show that this can be done. Oops, before we move on, this is me from the future. I wanted to make one little thing clear. On review, I noticed if we choose this Coolant gauge, which we're going to explain is always possible in a minute, if we choose this Coolant gauge, it is true that this becomes a scalar Laplace, inhomogeneous Laplace equation. And I said that you could solve it and you plug it in here and you end up with a wave equation. But I kind of extended it all the way over here. And if A was on this side, it wouldn't be a wave equation, right? The wave equation would only make sense if this is the only differential operator. But if you have this stuff left over with A, it's not a wave equation. But remember, it's the Coolant gauge. So this term, after the gauge transformation, is equal to 0, right? So this goes away too. And I didn't emphasize that point. This actually goes away as well. And so this whole thing goes away, which is what I correctly showed over here. It's just I didn't draw my lines very clearly over here to show how this whole thing goes down, right? And then the other thing that I want to mention is that, so these are second order differential equations, as I was saying before. To nail them all down, you need, it's just your standard stuff. You need boundary conditions or initial conditions. I mean, there are functions of time in here, so you need, initial conditions on the derivatives. And whatever structure for a given problem will articulate the boundary conditions. The gauge condition is actually a different condition. So when I was talking about the constant functions in the partial differential equations that will emerge that have to be dealt with, those are actually dealt with by boundary conditions. The gauge condition is altogether separate issue. Okay, so with those two caveats to sort of clarify what I was trying to get across, let's move on and begin these proofs that you can always find these gauge functions that will allow you to move into either the Coulomb gauge or the Lorentz gauge or any other gauge that's out there. In fact, we're going to start by talking about the axial gauge. Okay, so at the risk of repeating myself, but this kind of clarity, I mean, that's how I am clear. I'm clear instead of being clear, I'm clear because I repeat myself. But when we talk about a gauge transformation, we are switching from one gauge A to another by adding this gradient of a scalar field. And this is the gauge transformation. And notice that A is not gauge invariant. Sort of obvious because you're adding something to it and A prime does not equal A. Things are gauge invariant where if you make this transformation on A, that property remains the same, which is what B is. B is gauge invariant because B is the curl of A, and the curl of A and the curl of A prime give you the same B. So if you make a gauge transformation from A to A prime, B does not change. So B is considered gauge invariant. Now this is different than symmetry. Symmetry is a property where you have translational symmetry, rotational symmetry, symmetry under parity, symmetry under reflection, symmetry under time and reversal. All of those things make perfect sense in the context of electrodynamics, and they are firmly embedded usually in Noether's theorem. And those symmetries are not this. So we're not going to talk about gauge symmetry. We're going to talk about gauge invariance, which is a different idea. Symmetry is actually like a physical property of the system. Again, the gauge issue is this is some sort of mathematical artifact of the redundancy embedded in our math, is the approach we're taking, the rule set we're using. And likewise, a gauge transformation of the scalar potential is similarly executed using the same gauge function. And the electric field is also preserved under gauge transformations because when you execute the gauge transformation and convert V to V prime and A to A prime, you end up with these scalar function terms canceling out to zero, leaving it unchanged. So now we're going to talk about some gauge transformations that, three of them in particular. One that we've already looked at for the axial gauge, and then we're going to show the Coulomb. We're going to show that you can always find. We're going to show that you can always find an F to transform any gauge into the axial gauge, the Coulomb gauge, or the Lorentz gauge. So let's do that. Okay, so let's first look at this axial gauge, which we did last time. If we assume that our vector potential has three components, Ax, Ay, and Z, we understand that each of those components are scalars because they're the components of vectors, right? And they are each functions of x, y, z, and time. So each of these are functions of x, y, z, and time. So I'm looking for a gauge function of x, y, and z, and time, right? The time should be in there too. Put a little t there, right? Right, so we're looking for a scalar function, and we're going to take its gradient, and we're going to get the partial derivative of f with respect to x, the partial derivative of f with respect to y, and partial derivative of f with respect to z, and those are the components of the gradient of f, which is a vector. So now I'm going to choose f, this is a repeat of last lecture, right? I'm going to choose f so that it's the antiderivative of the z component with respect to z, right, which will introduce an arbitrary function of x and y when I do that. And so f still has this ambiguity into it, but the fact that the partial derivative of f with respect to z is going to be minus az by the fundamental law of calculus, right? So when I create a prime, I'm going to take, when I transform the vector potential A to A prime by adding this gradient, this gradient vector field, or the gradient of f, I'm going to get ax plus the partial derivative of f with respect to x, and likewise ay, partial derivative of f with respect to y, and az, partial derivative of f with respect to z. But this term, I can take that, the partial derivative of f with respect to z is going to be az, and this is going to go away, and that will cancel. It's going to be minus az, right, because of this minus sign right here that I included in the definition of f. And so this goes to 0. And this I just call a prime x, and this I just call a prime y, and this is 0. So I have found a condition where a prime z always equals 0, and this integral can always be done, the integral for f can always be done, and ergo I can always presume a gauge where the z component of a equals 0. Okay, so that's one down. Let's look at the other two. The Coolant gauge, right? So now in the Coolant gauge, I'm looking for a gauge where the divergence of the potential is 0. So I presume I'm in some gauge already. I've already got some vector potential. I'm now looking for the gradient of, I'm looking for a function whose gradient, when I add it to the vector potential I'm looking at, gives me a new vector potential, a prime, right? That's what this is. This is a prime. And I want that divergence to equal 0. So I'm just going to distribute the divergence through, and I get the divergence of a and the Laplacian of f. So if the Laplacian of f equals the opposite of the divergence of a, then sure enough, this whole thing will indeed equal 0. And that's exactly the condition. I have this inhomogeneous Laplace equation, which is scalar, right, because this divergence is a scalar. I solve this inhomogeneous Laplace equation for f, which can always be done, and now I have once I have that f, I create my a prime, and the divergence of a prime is 0. And this is why you can always shift into a gauge that has the Coolant gauge. You can always shift into the Coolant gauge. You don't have to hunt down f. You just say, well, whatever gauge you would do it in, an f exists where you can be in the Coolant gauge. So you just shift into the Coolant gauge based on this principle, that you can solve this differential equation in principle. And likewise for the Lorentz gauge. The Lorentz gauge, the logic is exactly the same. I'm now looking for a gauge a prime v prime where this term equals 0. The sum of the divergence of the vector potential and the 1 over c squared times the time derivative of the scalar potential, that sum's got to be 0. Well, let's make whatever gauge I'm in A, I'm looking for a function f, right? I'm in this gauge A, I'm looking for a function f, and this guy here equals a prime. That's the gauge transformation. And this is v minus f dot. That's the transformation for v. But this is v prime over here, so you end up with v dot and f double prime over there, right? So with that in mind, I'm now looking for the function f that satisfies this equation equaling 0, right? And it's not hard to do. I just separate the old gauge pieces, that a and the v, and I put that over here on the left, and I look for this function f on the right, and this stuff on the right has to equal this stuff on the left, right? Because I need this to cancel that, right? And again, not hard to do because this is simply the D'Alembert of f, right? This is sort of the wave operator. You know, this is d squared dt squared. That's this double dot. So I have the D'Alembertian coming in the opposite sign as the Laplacian, and that's usually written by a box, right? So this box operator is this D'Alembertian. So how would I do that? I would have to go 1 over c squared d squared dt squared minus del squared, right? That guy there, f, right? That's what this is here, right? And the sign over here changes because I move this stuff to the other side of the equal sign, so I pick up this minus sign here. Anyway, so now I have this equation to solve, and this equation, because I'm starting from a gauge that I presumably know, so I can always solve this equation. And once I solve that equation, and I use f to make the transformation from a to a prime, I have this expression. So I can always I choose my f that solves this equation, just like I choose the f to solve the Laplacian, Laplace's equation, the inhomogeneous Laplace's equation. I guess I have basically an inhomogeneous wave equation here is what this is all about. But they can always be done. So I can always find a way to move into the Coulomb gauge and move into the Lorentz gauge. And if I'm in the Lorentz gauge, I can shift to the Coulomb gauge, and I can find an f to do that. Okay, so that wraps up what I wanted to talk about today. We reviewed Maxwell's equations in their pure form. We took our hard-won potential formulation, stuck them into Maxwell's equations, and generated Maxwell's equations in potential form, which are now two second-order differential equations. And then we discovered that the ambiguity of these potential formulations, the gauge ambiguity, allows us to choose these conditions, these gauge conditions. And we can choose the Coulomb gauge condition because we can always find an f to transform us into the Coulomb gauge, and we can always find an f to transform us into the Lorentz gauge, where we get these nice, simple versions of Maxwell's equations, simple in a formal sense. But they're dissimilar, but they are simple. And you can quantize electrodynamics in either one of these two gauges, right? And maybe we'll explore that later. But the point is you never know what book you're going to land in when you study QED. You might study the quantization of it in the Coulomb gauge. You might study the quantization of it in the Lorentz gauge. And then I just went through the proof to show how you can always find this f. And the reason I did that is because I found that personally to be very difficult to understand when I first learned it, because the presumption was offered to us that because of this gauge freedom, you could always get to the gauge you want to be in. But they never took me through this very simple. It wasn't much of a step, was it? It wasn't too hard. You just have to understand that you can solve these differential equations in principle, given that all the fields are well behaved. Okay, so this is the core concepts of gauge transformations that are essential for QED. I think we're going to explore this a little bit more. We're going to talk about this in the context of quantum mechanics, and we'll discuss that ontology question a little bit more. But those lessons will be less and less critical for QED prerequisite and more for completeness of really coming to an understanding of the sort of elementary notions of gauge invariance and the significance of it. Okay, so we'll see you next time.